Okay, so it's been a little while since we visited the work that's we're doing on OSLF. So I'm gonna just give a reminder and then talk about some work that Mike and I have been doing to ensure that we get the right gadgets from the categorical constructions, which turns out to be surprisingly difficult. But we do have a method. Okay, so in a nutshell, we take a language spec. In the full version, we'll then adjust the language spec to have the operational stuff inside the rules. And in the even fuller version, these will be higher order algebraic theories. And so this would be a binding operation. But just for purposes of discussion, we would take a language, some specification of the language syntax. We take a specification of a collection. Then this is going to be predicates over that collection, and this is going to be predicates over the language syntax. Now, the tricky bit in all of this is that using category theory, what we would get as a solution for this domain equation is an object in the category where this is an endofunctor. So for example, if this is set, then the solution to this domain equation will be a set. It'll be a set built of subsets, and each one of these things will be sets, right? So this will be a disjoint union over set, and each of these will be sets. Now, there'll be sets of trees, but this thing itself will be sets. And what we really want is for this to be a tree and each of these to be trees, right? So this is where we're going to interpret the types that we're interested in, but we want them to be trees, not sets. And building a category of trees, while it is doable, is not necessarily the approach that we'd like to take. Maybe ultimately there's a natural way to do that. But there is a way to do it that I've kind of diagrammatically picked out here. So if we take T, this thing here, of this thing here, where we then go ahead and fill in the X. Oh yeah, I got rid of the X's at one point. Yeah, so this is, here we go. It's this one. It's this one, not that one. Sorry. So if we take this of this, right? Then this is a tree, and or this will provide a set of trees, which are infinitary. At least some of them are infinitary in nature, with predicates at every node in the tree, right? So one of these will sit at this location here, right? And then we'll have subtrees. Now, as long as we have a cover, now notice that if we do this naively, all right, we could always select the same predicate at every node, right? And so we don't get coverage of the language. So if we think of this as sampling from this, what we want is a kind of a fair representation, in the sense that we get a coverage of this domain equation. So we want to pick out those infinitary trees which ultimately give us all the possible predicates, right? So uh, uh, one way to think about it is that if you take the underlying set of this tree, that set is equal to the language generated here, or the solution to the domain equation. So we can think about here's the full spec, which is this thing here. We feed it into this box here, along with the filter criterion, which is what I just said about picking out trees that are fair sampling. That's kind of why I use the letter F here. This will pick out the domain equation, but really the domain equation we're interested in at the end of the day was just this one. Then we're going to find the fixed points, and then we'll find the fixed point, which is a set, or an object in the category where we're solving the domain equation, and then we apply the filter criteria to that, and that's going to pick out at least a set of trees. And if we're careful about if we add some extra information about ordering with respect to the grammar here, which we can do in terms of complexity, then we can pick out an equivalence class of trees which are sort of all the same up to some symmetries, and that's essentially what we want, right? You can pick out any representative in this class, and it will do the job. And so then this is a tree up to symmetry, and then each of these are disjoint. Each of these are different cases, if you're thinking about it in terms of programming language, for trees, and so that's the trick, right? So now this is interpreted as a tree as opposed to a set. And now it may seem like this sort of extra work for all the accounting, like 2 months ago, we'd written down this predicate domain equation, and it seemed like everything was just grand, and we knew how to do this in Scala. So it may seem like this is a lot of extra work for not a lot of payoff. But again, the point is that we want to map these things onto extant collections like GitHub, or a SQL database, or some boutique biological database which has its own format. And so we're demanding that whatever this is, that's really a spec for the data type where we find the semantics of each of these formulae, right? So these things are going to be hosted in some repository where we're keeping our candidate data. So whether they're programs or data specifications of other kinds of stuff, we want it to be in the shape of the collection that is native to that repository. So that's essentially the work that Mike and I have been doing recently, is to make sure that the solution that we get for these things is of this shape. So let me stop there and see if there are any questions.
So when you say T of X and mapping to some existing language, can we think about, for example, language have tuples, and we need to map constructors of these tuples.
So I'm not saying that it maps to a language. So again, let me draw another picture.
Because I'm thinking that this tuple can create trees in that sense.
Yeah, no, that's not what we're saying. They're separate.
Okay.
Okay. So what we're saying is the repo has a format. Okay. This is a data format, right? It's a schema for how it's storing data. And
are you already sorry, I want to ask, are you already talking about the terms in the language or?
Nope.
Okay.
No. This is a format for how it stores data, key value. Okay. What stuff is it storing there? It's storing this stuff. Right. So at some key, I'm going to find some value. What? A list of these things, or possibly, you know. So if we make these keys, then I'll find you know, a program here, and maybe underneath it some more programs.
And this can cover all of the structures until defining of the language. So directories, files, and all the other.
Whatever structure you're using to collect this data. That's the idea.
And this can be a file, right? Directory in the file.
Could be a file.
Okay.
But the point is that you've given us a specification of a recursive data structure, and in order for this to work, the recursive data structure has to have certain characteristics. So it's got to support. It's got to support certain things, but you know, we find that those things are supportable here in a data structure like tree. Okay, so essentially what we're saying is that this thing, whatever it is supplying what set would normally supply in terms of some of the logical operators. And this thing is supplying structural operators. Like, so just like we know we can do a kind of sorting of program terms by checking their structure. So pattern matching is fair game for logical operators, right? That's, you know, like recognizing that a program has a for comprehension shape, or recognizing that a program has a parallel composition shape, right? Recognizing program shape is a part of the logic, just like collecting programs is a part of the logic, right? And then when we encode the operational semantics, then recognizing the steps a program can make becomes also a part of the logic, right? And so making sure that the machinery that's used to calculate the fixed point of this domain equation gives us something of this shape is important. Yeah. So that's why we're doing what we're doing. So any other questions?
So in the P of n, we will recognize the structure of the structures that some language supports, right? Yes. Different case classes.
Yes, this is the grammar for your model of computation, right? Right, and I've right. So a more realistic version of that is not there. Is it here? Yeah. So the more realistic version of that is here. So we start with this, then we transform it to this, where we've also got a red X's that are part of this thing. And then in the case of row, the red X's would be a vowel, com, and par. Right? And so we start with this simple thing. We add this to reflect the operational semantics, you know, and adding these equations, right? And you can do the same thing for lambda, right? And then the other elaboration, just to be super clear, is that it won't just be something like this. It'll be a higher order algebraic theory. So we have we have enough contextual apparatus to specify binding operations like the for comprehension, or the new construction in pi, or the abstraction in lambda, or blah blah blah, right? So that's slightly more realistic, okay? But the point is that all of that is still amenable to the same kinds of solutions for fixed points. So we'll still get a fixed point which specifies this thing. And then we want to do this construction over top of that to get notions of predicates, right? So given a collection, we do the collection of collections, and that's going to give us the logical operations here at this level. And then we do L of these two things. And then we go through this filtering process to select the equivalence class of gadgets that are going to interpret these things.
With a fixed point operator, we can use it for structural and for structural like
for everything. You'll get everything,
and also for operation semantics, right? For
correct, but because we did this, right? Oops, is it this one? Wait, where is it? Can I move it up here? No. All right. So this is, yeah. Because we did this, right? We'll be able to interpret formulae like this.
So operational semantics is somehow like higher order fixed point in a sense.
No, it's exactly the same fixed point. That's the point, is we put it right, the fixed point, because we've turned operational semantics into syntax. It's just syntax.
Oh, so this is important. So I see. Oh, so now I think that I have better understanding of source and target, because this fixed point is not higher order. It's this is why this is the source and target.
Correct.
I see. Cool.
Yeah. So you'll notice that, you know, there's the only recursion that happens is underneath here, right? So underneath here we'll get P from here, and underneath here we'll get N and P's from here, right? And then underneath here we'll get P from here, right? So I mean, in some sense, these are kind of off to the side, and the only recursion is because inside these we have these. But right, but none of these mention R's. So you can see this as divided into two bits, right? Just the language itself, like all the expressions in the language, together with expressions that represent the operational semantics, right? So the red X's. So
where I'm thinking where we know how I'm thinking where we know how to when we need to expand
this is the infinite tree, right? It's all of it. It's all computation ever possible, right? It's the Library of Babel.
Yeah. So we are starting from somehow from the root, and then we can expand how much we like in the, especially if we have some reduction.
This is one step, right? This is one step. So you go as far as you need to go. So if you're looking for deadlocks, right? Basically, you're looking for cycles, right?
I see.
You're looking for certain kinds of cycles.
And now with the predicates, we are describing the types of this fixed point. So what we can expect if we go into this direction.
Correct.
Something like that.
Correct. It's the types.
I see. Nice.
Okay, so that's the this little bit was the extra work that we were doing to make sure that we got the right. And then we got solutions that were of the collection type as opposed to of set type.
You mentioned for the tree underlying set. This just means set inside the set, nested set.
If you just wander down and collect up all of these things, right? You're either going to hit a leaf, right? Or you're going to hit a tree, a node with some subtrees. The nodes are the only place we're storing data, right? So you just go and collect all the data, right? Just wander the tree, collect all the data in a set, right? So it's a fold. It's a fold over the tree that returns the set.
I see. I see. So like all the leaves, right? Because
no, not the leaves. The leaves are empty. The leaves are empty. It's all the nodes. This is a different kind of tree. It's not a tree with a fringe, right? It's a tree where the data is stored on the internal nodes. The leaves are empty.
Oh, okay.
And those nodes, are those in infix or Polish notation?
It doesn't matter what notation they are, right? It's parametric.
Okay, so it's still going to be like a consistent graph.
It's just this is just a normal tree spec, right? If you were to write down a tree spec in Scala or C# or F# or OCaml, right? It looks like this, right? The Scala code is a let's see, class. Stop it. No. Class tree X, oops, right? And then you have case object empty tree, right? Oh, fribble. I'm not going to do it that way. Case class. We'll fix that up later. Empty tree X. And then let me move this over a little bit. and it's got, and this one extends tree. Right, that's this branch, right? And then the other branch is case. Come on, stop. Not helpful. Not helping. Case, class, node, extends tree,
Accepting.
right? And then tree of X, and then it has inside it the children. So it's got.
But not can have constructor arguments.
Yeah, exactly. Yeah, you can just do it directly. Exactly.
Yeah.
Yeah.
With
yeah, X is of type X, and a child or progeny
tree of F. Yeah.
is type list tree
list.
right, and then close that up. There you go. There, that code is exactly that line.
Okay, great.
Okay, so anyway, so that's it. That's essentially what we've been doing. So we're at the point now where we'll go do one more pass over this, make sure the negation is well sorted out, and then we can begin writing up the results. So it's at the point now where we can, as you can see, we can implement this directly in Scala. And so my recommendation for an implementation path is to take Scala plus Kiama. So someone can take a Kiama spec for a language, and this would be roughly equivalent to a K framework spec. And then because Scala has a reflection on types, you could actually, eat the Kiama spec and generate a set of types for that language following this algorithm, and you will get the proof. You'll get both the model checker and the proof theory, right? So the model checker will look, the type checker will look like this. These will be the examples of the rules that you'll get for type checking. And then, you can literally run it against the Kiama spec of the language. And if you want to go further, then you'd have to wire up a Kiama spec to something a little bit, to some kind of transducer, which would eat existing language syntax in legacy repos like GitHub and things like that.
And higher order abstract syntax we get with Kiama, right?
No, Kiama would have to be extended with the higher order abstract syntax. So it has a way to do binding, but that's not as general as higher order abstract syntax. So it would have to be hacked to do that.
Mm-hmm. And when you say that, this basically means we need to bring in our implementation for binding. And can this
Correct.
be just the Bruin indexes as like a
No.
simple?
No.
Okay. Mm-hmm.
The higher order abstract syntax is doing more than De Bruijn indices.
Mm-hmm. Can you just briefly sketch how this would look like?
I will refer you to the paper. Hang on a second.
Mhm, mhm. But this basically means we are using existing bindings in our host language to and somehow lift them on this level that we need.
Sorry, I was just looking up the paper. 1 second, then I'll answer your question.
Mhm.
This does not look familiar. So I haven't read this one, but it looks good. So I'll send you a link to this, and then I'll find the one that I think is paradigmatic. Here you go. So here's, let me stop sharing for a second so I can get to the chat. There you go. Okay. So there's one, and let me go back and look for the others. Is it this one? No.
And what about this one? This is from Frank Fanning and Conal Elliott.
No,
That
that's
seems
not it.
pretty old.
That's not it. I mean, it looks like a.
Do you mind if I ask a couple questions about Casper?
1 second, please. All right, I'll have to find the paper later. It's not showing up. That's weird. Just hang on, let me try one other thing. Marcello Fiore. Why is it not showing up? Here we go. I think this might be it. Yes, I think this is the one. Let me just double check. Just looking for the rules. So there we go. There's syntactic theory. Here we go. Yes, this is it. This is absolutely it. Okay, yeah, here you go. All right. Okay, there you go. There's the other one. Okay.
Sorry,
okay.
can I just
So
ask
now,
you, why are you so specific about that? Because I'm a little bit confused because there is lots of paper about higher order syntax.
Because
What?
not all of them refer to the same thing.
Oh. For me, this is difficult to separate.
Yeah, exactly. That's why I'm giving you the goods. Yes.
Yeah.
Okay. So
Yeah.
now, Tomislav, you had a question before I was looking, or while I was looking for the paper, and then I'll get to Frank's questions. Your question, Tomislav, what was it? Remind me.
Sorry, I don't recall right now.
Okay, no worries. Frank?
Yes, I know in Casper the composition of staking or validating for participating nodes, that comes out to be graphical in representation. But I still don't know how the slashing effects work, where, so the general principle of proof of stake is that each node on the network is able to stake a certain amount of cryptocurrency in order to profit from an exposure to gain. Yet there needs to be a negative balance to that. There needs to be a negative reward so that to avoid users acting manipulatively. And I was wondering if Casper had ways yet to deal with slashing, so that if a node was acting maliciously, the rewards would be slashed from their 0x account.
Yes. Yes, this has been implemented in our chain for several years now.
All right. I like the idea of adopting, moving away from proof of work and adopting a more sustainable method. I know that really aligns with our chain's method, our chain's mission, combating global climate change, creating a more sustainable atmosphere, and having a general positive effect on ecosystem at large. Yet I wanted to say that the principles behind the code are really the driving force of what's going on.
Yeah, that's right. That's right. So you missed a couple of good ones where we were talking about finalization and what one does in the case that you have the network partitions where the one group of validators can't see another group of validators, and how you handle finalization in that case. So we will be rolling out a version where the simple version of the algorithm where you don't deal with network partitions, which is the most common case in today's hardware and networking situations. But on the heels of that, we'll be rolling out a version where we do deal with network partitions, and probably in between there'll be a .1 release where we just kick validators who are perceived to be tardy. We kick them to the curb and say, at least for this epoch, you can't play. We won't slash you, but you can't play.
I've become accustomed to proof of work. I was so used to the idea of a decentralized database. Imagine a global data center having each computer, each piece of hardware running that same Bitcoin core software, and then keeping up with validating the network. And it's an incredibly inefficient use case of energy. I think just starting from thermodynamics, it's better to put people's own word of mouth, in this case, using this information technology to place their trust of money instead of computationally using up energy.
Yes. Well, I mean, certainly proof of work is incredibly wasteful. I think we all agree with you there. Okay. Thank you, everyone. Go ahead.
My question was related to higher order syntax. Does it mean that we expose bindings from the host language, like lift the bindings that we have and use them?
I don't know what you mean by host language, but if you're talking about implementing Lambda in Scala, no, you're not exposing in the Lambda specification how Scala does it. Definitely not. That would not be portable.
I was thinking that reusing the variable bindings that we have in the language that we are writing the implementation.
Right. So you're writing an implementation of lambda calculus in Scala, and you're trying to use the Scala variable bindings for the lambda stuff. No, definitely not. Definitely not. That's not portable. No, the whole point of the higher order algebraic abstract syntax is that you have a complete and sufficient framework in which to do the whole thing. All the apparatus is right there. It's just machinery. There's no magic. Right. So like using the binding from the outside language or the language in which you're implementing would be the equivalent of magic. It's like, we don't know how to do variable binding, so we're going to let this guy who knows how to do it. Right.
I see. Okay. So because some of these some of the papers that I was reading, they are doing exactly that. They're saying, "Oh, we are not implementing this. We're just using what we have."
Yes.
So this is my understanding. Okay.
Yeah. So no, we're not doing that. That's why it was very important to send you the right papers.
Okay. Okay.
Yeah. All right. Thanks, everyone. Appreciate your time, your engagement, and I'll see many of you in Dev Stand Up in a little bit.
Great. Thanks, everyone.
Great.
Thanks, Greg.
See you.
Thanks for your time.
Bye.